Hi, my name is JJ Wertkin, and I will be talking about the ray tracing algorithm today. So, a little overview. This algorithm originated in the 16th century and was invented by Albrecht Dürer. He came up with the idea of the Dürer's door technique, which described an apparatus using a thread attached to the end of a stylus that an assistant moves along the contours of the object to draw. The thread passes through the door's frame and then through a hook on the wall. The thread forms a ray, and the hook acts as the center of projection and corresponds to the camera position in ray tracing. So ray tracing uses visual images constructed in 3D graphics and is also a rendering technique that aims to simulate light bouncing off of objects. So you're able to get a really clear picture through this implementation and also not have to worry about working with background. So there is essentially a 6-step process when you're actually defining or implementing your own ray tracer algorithm. And to start off, the first step would be defining your scene. So ray tracers essentially simulate light rays to render a 3D scene. Before we can start doing that, we need to define the scene that we want to render. For this case, it's rendering a 2D version of a 3D triangle. The second step is calculating the planes. So triangles are flat and two-dimensional, and we can imagine a triangle as a small section of an infinite plane. So during this process, we would calculate the planes, and by calculating them by finding the angle of the plane's normal line. And the normal line is the line that is at a right angle to the plane. To get the angle of the normal, we will use the cross product of the two vectors. The cross product is an algebraic function, and when given two vectors, outputs a new vector, which is orthogonal to both. The next step is actually calculating the ray lines. So this is when you usually start simulating the rays. And the vector representation of a line, including both position and angle, is very important in this step. In step 4, we actually find the intersect where rays meet with planes. And we're finally basically ready to simulate our light rays. So we know that where our light rays start, where they're going, and where everything they might hit. And all that's left to do is actually simulate the path and find out what each ray hits. So in step 5, we are trying to find the filter intersection points. So when you're going through a ray tracing algorithm, in this case, trying to find the actual triangle, not all intersection points will actually be valid. So we only care about the ones that are actually inside the triangle. And then finally, in step 6, is rasterizing the rays. So each ray can only intersect with one triangle. So we need to find the triangle that gets hit first. And then for this implementation, we set the pixels brightness to a certain amount, and then meaning pixels that are closer to the camera are brighter. And then any rays that don't intersect result in a black pixel or just are out of air. So that'll basically represent the shadow of the shape. So another way you can look at this algorithm is represented through this pseudocode. So just going through the top here, so the ray tracing algorithm takes an image made of pixels, and then for each pixel in the image, it shoots a primary ray into the scene. The direction of that primary ray is obtained by tracing a line from the eye to the center of that pixel. So then once we have that primary ray's direction set, we check every object of the scene to see if it intersects with any of them. In some cases, the primary ray will intersect more than with one object. When that happens, we select the object whose intersection point is closest to the eye, or in this case, the camera. We then shoot a shadow ray from the intersection point to the light. If this particular ray does not intersect an object on its way to the light, the hit point is then illuminated. If it does intersect with another object, the object casts a shadow on it. So if we repeat this operation for every pixel, we obtain essentially a two-dimensional representation of our three-dimensional scene. There are also different versions of ray tracing. So, for example, forward ray tracing follows the light particles or the photons from the light source to the object. So, although forward tracing can be most accurately determine the coloring of each object, it is also really highly inefficient, just because it's going from the light source to the eye, which is also not very realistic. Another version of ray tracing is backward ray tracing. And so after the ray tracer allows the light ray to bounce around, it figures out the exact coloring and shading of that point in the view plane and displays it on the corresponding pixel on the computer monitor screen. Backward ray tracing is also known as eye ray tracing. So there are a few advantages and disadvantages to using ray tracing. Advantages include more realistic than rasterization, so it works in a more realistic way, especially when you're thinking about it from eye to view plane. It's also easier to work with non-planar surfaces such as cones and spheres. And it is also really important for rendering reflections, and shadows. The disadvantages include slower than rasterization and scanline tracing. So the computation complexity for this algorithm is the square of the object number. So the bigger the object, the longer it's going to take to compute, and also requires the scene geometry to be stored in memory, which can take up a lot of space when computing. All right, thank you for listening.